Hello, welcome back to Short Text 331. Today we're going to continue our discussion of determinants. So this is determinants part 2, and I want to talk about two applications today, or two connections to the previous video where we defined determinants. So recall that we have this recursive definition of determinants, which is often called the Laplace expansion, where the determinant of a square matrix A is written as a sum from j equals 1 to n of the element a1j of the matrix times minus 1 to the 1 plus j times the determinant of a1j. And this determinant of a1j, this a1j is a matrix obtained from A by removing the first row and the jth column. Now, why the 1 here, here, and here? That implies that we're talking about the first row, element j, the same one here, and the same one here. We remove the first row and the jth column. Well, there's nothing special about that. We could have used 2 or 3 or n or any row. All of those will give you the same result, it turns out. Now, regardless of that, this definition motivates us to define the so-called cofactor matrix C. So that matrix C is defined by its elements given in this formula. So you have the matrix element ij, so Cij is minus 1 to the 1 plus j, and that's the same minus 1 that appears here, but now we put an I instead of a 1, times the determinant of Aij, which again is the determinant of A, but you've removed the ith row and the jth column. Now, using this matrix, we're going to rebuild a matrix product using this formula in this way. So if you take the matrix product of A with C transposed, so remember C transpose is a matrix that has elements Ji instead of Ij here. So C transpose Ij is the same as here, but with I and J exchanged. That's another way to see it. And so this product, it turns out, then we take this following form. So the product of A with C transpose element Ij will be the sum over a new index k from 1 to n of A, Ik, C, Jk. So notice that I didn't write C, Kj. That would be the product of A with C, but we want the product of A with C transpose, and so that's why I wrote C, Jk, the same order as here, Ik, Jk. So now let's write it down. So now we have the sum and the sum again. Aik stays the same, and now we write Cjk according to this definition of the cofactor matrix. And so that's minus 1 to the j plus k times the determinant of Ajk. And it turns out, if you look at this formula carefully, that if I is equal to j, then you obtain the determinant of A. So if I put I equal to j here, I put, for example, 1, 1, 1, then I recover this formula. Or 2, 2, 2, I get the same result. And but when I is different from j, it turns out that's 0. And so what we get then from this product of A times the cofactor matrix transposed, which by the way is the same result as for C transpose A, is that they're both equal to the determinant of A times the identity matrix. So again, remember, for each I equal to j, 1, 1, 1, or 2, 2, 2, or n, 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 any of those, then we get the determinant. And so we get basically something proportional to the identity, as shown here, times the determinant of A. And so this tells us that the cofactor matrix has a lot of information about the inverse. In fact, if we divide across here by the determinant of A, then we have this equation, A times C transpose divided by the determinant of A is equal to the other order, so the reverse order where C transpose divided by the determinant of A goes first, times A, and that's equal to the identity. And what this tells us then is that C transpose divided by the determinant of A is playing the role of the inverse. In fact, it is the inverse. So A inverse, it's a cofactor matrix transposed divided by the determinant of A. And so that's what I wrote here. The inverse is equal to the cofactor matrix transposed divided by the determinant. Now that would be a really silly way to calculate the determinant, to calculate the inverse of A. You really wouldn't go this way unless you're dealing with matrices that are very small. So 2 by 2, 3 by 3, and then automate it to 4 by 4 and 5 by 5. But if you really want to calculate an inverse, you would use a completely different algorithm that we'll see in a future video called LU decomposition, or other types of algorithms that are out there. You would not do it this way. And the reason you would not do it this way is the same reason that we discussed in the previous video when talking about the determinant. That is that the determinant involves, at face value, n factorial operations. And so that is very expensive to do. You would not do it explicitly in this way. Now, if you have a better way to calculate the determinant, or if you have a better way to calculate the cofactor matrix, then you do it that way, right? And in a way, this is what other algorithms like LU decomposition and such actually accomplish. Now, I want to clarify something about this thing that I pulled out of my head. Basically, I told you, let's define this cofactor matrix, and then it turns out that this is a determinant and so on. So where does it really come from? One way to see where it comes from is that you can regard it as the application of Cramer's rule to the problem A times matrix equals the identity. And so the problem of finding this matrix M is the problem of finding the inverse, because the inverse is a matrix that accomplishes this. But it's also a way to see this as the problem of finding that inverse as a problem of finding the columns of M. So M is made out of column vectors in this way, n of them, and an A times M1 has to give you the first column of the identity, and A times M2, the second column, has to give you the second column of the identity, and so on and so forth. And so in reality, what we're doing when we're finding the inverse of A, or when we're attempting to solve that problem, is we're attempting to solve n different linear systems all at the same time. So we're trying to solve this linear system where AM1 is equal to E1, then AM2 equal to E2, and so on. We're trying to solve all of those. And if we solve all of those, then we have the inverse, because we just put the results of M1 and M2 and so on in columns here. We assemble all them, and that is the inverse by construction. It turns out, or rather what our formula tells us regarding the cofactor transpose divided by determinant of A, that formula tells us that the first column of M1 has elements that go like this: minus 1 to 1 plus I times determinant of 1, A1I divided by the determinant of A. M2 has elements that follow the same rule. And how is that connected to Cramer's rule? Well, if you focus on this problem in particular, for example, AM1 equals to this E1, where there's 1 and then zeros after that, then Cramer's rule tells you that the solution to that problem is simply the determinant of this matrix, where I've replaced the first column. This is the determinant of A, where I've replaced the first column by E1 and divided by the determinant of A. So if I do that calculation, then I will obtain this result here. And if I is equal to 1, that's the first element of M1. If I now go for I equals to 2, the second element of M2, then it gives me the element M21 of the inverse. And I have to replace the second column of this determinant by this vector E1. And so if I do so, and I calculate this determinant, then you will see that you will end up with the same formula, but now with I equals 2, because A1, 2, it corresponds to precisely that, removing that second column and the first row, and doing that determinant that results from that, dividing by the determinant of A. And so that's basically what it is. So then once again, the fact that the inverse is simply the cofactor transpose divided by the determinant of A is something you can regard as the careful and systematic application of Cramer's rule to the sub-problems of finding the columns of the inverse one at a time. So here I focused on the first column of M, but you obtain the same result if then you go on and you see what happens for the second column and the third column and so on and so forth, and you will see that it all comes down to the cofactor matrix divided by the determinant. And you can already see, of course, that the division by the determinant is something that appears very naturally from Cramer's rule. If you enjoyed this video so far, please like and subscribe. And if you're looking for a tutor in physics or math in English or in Spanish, you can contact me at shorttext331@gmail.com. If you're looking for the PDFs attached to these videos, you can find it in the description. I'm going to link all the PDFs to the descriptions of all the videos from this point on. Now, I want to switch to another application. Given an n by n problem, so of this form, what we call a homogeneous linear problem, set by matrix B, we always have a solution to this problem in the form of x equal to 0, of course. So B is a matrix, is a linear operator, and so linear operators always map 0 onto 0, and so you can always put x equal to 0 here and solve the problem. Usually the question when you have a problem like this is x equal to 0 the only solution, or are there other solutions? Well, if the determinant of B is not equal to 0, then as we have seen in a previous video, then B has an inverse. And so x equal to 0 is the only solution, because if B has an inverse, you can multiply both sides of the equation by B inverse, then you get B inverse B, which is the identity, so you get x equals to B inverse times 0, but B inverse is a linear operator as well. Remember, the inverse of a linear operator is itself a linear operator, and so it maps 0 onto 0. And then, in short, there's no other solution than x equal to 0, if the determinant of B is non-zero. Now, if the determinant of B is equal to 0, then there will be an infinite number of solutions, because the columns of B are linearly dependent. And so we will not have enough constraints that force x equal to 0. In other words, we will have a bunch of equations determining the possible values of x, but not enough equations, not enough independent equations to force all the elements of x to be 0. And so we'll have an infinite number of solutions, and they will be in general non-vanishing. We will still have x equal to 0 as a solution in this case, but we'll also have non-vanishing solutions. And it turns out that this is a useful thing to know. We often think, oh, well, we really want to be in a situation where the determinant is non-zero. Because if the determinant is non-zero, then we can guarantee that the solution exists, not only exists, which we already knew, but is unique. But it turns out this is also useful, determinant of p equal to 0, and it's useful when calculating the so-called eigenvectors and eigenvalues of a matrix. And this will be discussed further in a future video. But for now, just in passing, I'll give you the definition. So the eigenvectors of a matrix M are those non-zero vectors, and the non-zero is important, non-zero vectors such that there's some scalar number lambda for which matrix times the vector is equal to that constant lambda times the vector. And there may be different values of lambda for which there exists some vectors for which this happens. So those things will come in pairs. There will be a vector and a number, scalar, and the vector is called the eigenvector, and the lambda, this constant, is what's called the eigenvalue. And so each matrix will have pairs of eigenvectors, eigenvalues, several of them typically, and that satisfy this equality for some value of lambda and some specific vector or set of vectors. So how do we find those? How do we find the lambdas and the v's for a given matrix M? How do we solve this problem? To solve this problem, and by the way, I'm going to tell you more about the applications and why this is interesting in a future video, but to solve this problem, to find these eigenvectors and eigenvalues where you apply M and you just get a constant times the original vector, first we put this on the other side of the equation, and this is how you write it. So M minus lambda times the identity times the vector is equal to 0. So here I inserted an identity. Imagine multiplying by the identity here. The identity doesn't do anything, but it gives me a matrix form where I can assemble this together into one matrix. So now M minus lambda I, or minus lambda 1, is one matrix. And what this is telling us is simply subtract lambda from the diagonal matrix, the diagonal part of the matrix M. And so now we have a problem of solving this equal to 0. Well, we always have the solution that v is equal to 0, but that's not the solution we want. We do have it. V equal to 0 is a solution of this problem, but it's also a solution for any lambda whatsoever, and that doesn't tell us much. We want the non-zero vectors that do this. And so to have v non-zero, we must then force the lambda to be such that the determinant of M minus lambda 1 is equal to 0. Again, to have v non-zero, to have possible solutions that are non-trivial, non-vanishing vectors, then it must be that lambda is such that this determinant is equal to 0. In that case, then there will be such solutions. In fact, there will be a large number of them, and we have to discuss how we're going to treat those. Now, this is called the secular equation, and it fully determines the eigenvalues of M. So the allowed values here, you should say the allowed values of lambda for a given M. And so to give you an example, so if M is a simple 2 by 2 matrix, 1, 1, 2, 0, then M minus lambda 1 is simply 1 minus lambda, 1, 2 minus lambda down here. And so now we're ready to take the determinant. And so if we take the determinant of this matrix, we get 1 minus lambda times minus lambda. That's this first term here, lambda times lambda minus 1, canceling the signs, and then minus 2 times 1. So this is minus 2 over here. So now we have to set this equal to 0. And from there, we get a quadratic equation for lambda. So if you distribute here, you get lambda squared minus lambda minus 2 equals 0. And that's a quadratic equation for lambda. If the matrix is 3 by 3, you're going to get a cubic equation. It's going to be more complicated. If your matrix is any realistic application matrix, like 100 by 100 or 1000 by 1000, then of course it's going to be very hard to set up this equation and calculate the eigenvalues. And that's a whole problem in numerical linear algebra, how to calculate the eigenvalues efficiently, or the lowest eigenvalues or the largest eigenvalues, whichever you might be interested in, given that the problem is very large. And we don't know in principle any formula for a very high order polynomial that will result from this. So this will always give you an algebraic equation for lambda, so a polynomial, a complicated polynomial of as high order as the matrix. So if the matrix is n by n, this will be a polynomial of degree n and equal to 0. And so you have to find the roots of that polynomial. And so this is what the secular equation tells you. And by the way, that polynomial is called the characteristic polynomial. But once you have that, then you have the lambdas. And what do you do then? Well, then at that point, you can go back to this equation, and with the lambdas that are allowed, you insert it in here and you try to solve for the v's. But I'll leave that for a future video on more specifically eigenvectors and eigenvalues in general. If you enjoyed this video so far, then please like and subscribe. If you're looking for a tutor in physics or math, in English or in Spanish, I'm happy to help you. Please just contact me at shorttext331@gmail.com, or you can leave a message in the comment section below. And that's all I have for you. See you next time.